We can see your screen. So it's a pleasure to have Giulia that she will talk about the Mellin Transform in one-dimensional CFTs. Please go ahead.
Thank you very much for giving me the opportunity to present this ongoing project with Lorenzo Bianchi, Gabriel Diar, and Valentina Porini. I want to start by briefly introducing the basic aspects of CFT, some of them. And in general, in CFT, we have two kinds of operators, the primary operators and the derivatives of the primary, which are called descendants. And as in every CFT, in a QFT, we can just define an operator product expansion by taking two operators really close to each other and expand them. And in this case, it's going to be an expansion over the primaries. We're going to have this power law dependence. And this expansion is going to have a finite radius of convergence. And in particular, this Cij, K, and this delta are obtained from 2-point and 3-point function, correlation function, and are the scaling dimension of the operator of the theory, and the 3-point coefficient, which are also called, the structure constant of the operator algebra. And the set of all the scaling dimension and the Cij form what is called CFT data. And with the full knowledge of the CFT data, we are actually able to compute any endpoint correlation function by reducing them using the OPE. Another key ingredient is the crossing symmetry, which is an important and really powerful constraint that we can impose in our CFT, and it's an equality between two different OPE channels. We are going to be actually interested in defect CFT, and defects are just modification that we can introduce in our system that preserve just part of the conformal symmetry. And conformal defects are interesting because they can actually probe some information about the theory that are not really accessible to correlation function of local operators. One-dimensional defect CFT, because every higher D CFT can actually be interpreted as a one-dimensional CFT, and also because it's a simpler but still constraining enough setting for testing ideas about higher dimensional CFTs. And now I'm going to present you an example in ADS2 CFT1. This is part of the more general duality between ADS5, process 5, and N=4 Sobranian Mills. And in the setup, we can just pick one of this Maldacena-Wilson loop, which is the Wilson line. And this Wilson line is going to be infinite and is going to preserve the maximal amount of symmetry possible, which is half of them. And here you see how they are broken. And in particular, the 4-dimensional conformal symmetry, so SO2, 4, is broken down to the 1-dimensional conformal symmetry, SO2, 1. This is the setup. And so we have ADS5, the boundary of ADS5, and we are going to identify this Euclidean time with this line that defines the operator. And this line, a strong coupling, is going to be dual to an open string minimal surface, which is ADS2, which ends precisely on this line. The peculiarity of this setup is actually that the CFT correlation function are expected to be reproduced by some ADS2 amplitudes, string amplitudes, that are just evaluated in the string sigma models. And we have this correspondence between O, the operator in the CFT, and X, some string coordinate that are actually small fluctuation transverse to this ADS2 minimal surface. And if we want to compute, for example, a 4-point function, we can expand in the inverse string coupling via this ADS2 Witten diagram. And here you see one of them, which is a contact interaction. And from here to here, we had just a conformal transformation when this boundary is mapped to this current circle and the bulk ADS2 is now inside. And this is actually the setup that really raised our interest in another tool that we can use, because it's also a rich setup in the interplay of different techniques that can be used, apart from Witten diagram. And this tool that we thought of using answered this question. So if there is a momentum space representation of this CFT correlator, that simplifies this computation. So a sort of Fourier transform in hyperbolic space. And the answer is yes, and this is precisely the Mellin transform that was introduced by Mach in 2009 in this context, and it is a very useful tool. And because it also delivers a representation of this conformal correlation function that makes the scattering nature more transparent. These are the properties that we expected from this Mellin transform. So to deliver a simple representation of the CFT correlators, to be crossing symmetric since the CFT correlators are, it will also be meromorphic, and so there will be a correspondence between the poles in the Mellin and the exchange OPE operator, and it will be polynomially bounded. I want to show you just the higher dimensional case, one of the most studies. So in 4 dimension, a 4-point function of identical scalars will be expressed in this way using the Mellin. And so we have an integral over these 2 independent Mellin variables, gamma 1, 2 and gamma 1, 4. And I'm going to just explain in a second what it means independent. Here we have our Mellin amplitude times some factors of gammas, and all these factors can be intended as reduced Mellin. And we have the 2 cross ratio to some powers of this independent Mellin. They are independent because taking a general gamma ij, they have to satisfy some constraint. And to solve this constraint, we introduce some fictitious momenta variable. You see here the identification. And we notice that this condition just turned out to be momentum conservation and on-shell condition. And we see the similarities with Mandelstam variables. If we are concerned about the contour, so if we try to integrate in gamma 1, 2, we have to consider these 2 contributions, so from these gammas and from these other gammas, and the contour must be taken such that this semi-infinite sequence of poles are left completely to the left or the right of this contour. And the nice feature of this Mellin transform in this case is that the contact with the diagram is just a constant. So this is just a constant. And this is really interesting. And so we tried to extend this Mellin transform, this concept in 1D. And in 1D, we expect to have just, from the kinematics, just 1 Mandelstam variable. And this is what happened indeed with Mellin variable. We are going to have just 1 independent. And the strategy at first was trying to reduce the higher dimensional 1 by imposing the diagonal limit. So here chi is just the cross ratios, so the only cross ratios in this case. But these integrals are actually hard to perform. And indeed, you have no guarantees in the end that you get a simple Mellin amplitude. And so we try to define it from scratch using some general form. And this ratio is actually suggested by imposing this diagonal limit in higher D. And we try then to constrain that with Gaussian symmetry and also with the OPE. But this turned out not to be enough because you don't get a unique Mellin transform and not even simple representation of the correlators. And so we tried to look for those Mellin definitions that gave us the simplest representation possible. And we ended up finding this. And we applied that on D-bar functions, which are just those contact interaction. And you see that for identical scalars, this is how they look like in cross-ratio space. And this is the Mellin that we were able to get in Mellin space. So this product of gammas and some constant, or in this case, it's just a polynomial. And we were able to find a closed form for the crossing invariant D-bar function. We also checked that it's crossing symmetric, but it's also pretty visible. And this is the crossing. And we checked we see that it's a meromorphic, and we checked that the position of the poles in the Mellin were actually corresponding to the exact exchange operator in the OPE. And we also checked the polynomially boundedness via a theorem that regards like 1-dimensional Mellin transform. And so in the end, we saw that these actually 1-dimensional CFT are really interesting playground, and where the starting point that raised our interest in this Mellin formalism. And this higher dimensional experience teaches us that this Mellin space seems to be the natural framework in which we expect to simplify computation and expression of correlators. The 1D reduction of the Mellin is really subtle because we cannot directly derive it from higher dimensional case, but we propose a consistent definition of it that satisfies the expected properties. And now we are focusing on various CFT1, and we're trying to extract the CFT data directly in Mellin space. But we can also wonder about higher loops of those CFT because computation can be pretty simple at 3 level, but they will increasingly be harder at higher loops. And we can also ask about flat space limit, which is connected to the integrability of the system, because we expect that using a simpler representation of the correlation function may bring up some hidden feature of this CFT's correlation function. Thank you.
Thank you very much, Giulia, for the nice talk. Are there any questions for Giulia?
I made a question actually.
Please, Alessandro.
So I didn't quite get you started from the example of the half BPS Wilson line. I didn't quite get how the supersymmetry and the large N play a role in your construction, or if they don't play a role at all because the construction is more general. Are you using this to derive your results or not?
No, this was just, it's just a setup that more like general setup that raised the interest in the Mellin, but now we are not really using this setup to derive any constraint. We're just applying that to more basic CFT1, because the goal will be to just arrive to more complex CFT1, but now we are trying just with the 5 to the 4th, for example.
So it's just a SO 2,1 symmetry that you're using.
Yeah, now it's
and other axioms like crossing and so. Thanks.
Yes.
Any other question for Giulia? So maybe I have a curiosity. So one of the defining property of the Mellin transform in higher dimensions is precisely that the simplest contact interaction, phi to the 4th, is just 1, is just a constant. So basically you say so can you use this to motivate that your Mellin transform is the unique Mellin transform that satisfies this property, or you had to impose some other conditions? So is this analogy correct also in 1D, or there is something different?
It seems that in 1D it's not really, like, you are not really expecting to get just a constant. And in this case, indeed, we have just here a constant and a polynomial. So it's not really just as simple as the higher dimensional case. But it seems that in this case, which is the definition that we found more, like that gives the simplest representation for the bar function, in my opinion, is also connected to the fact that this presents some kind of other symmetries, because it's not only crossing symmetric, but there is a connection between the two kernels of the Mellin and the anti-Mellin. And so one is the crossing symmetric of the other one in this case. And it seems that this kind of extra constraint just give us the simplest possible representation.
About you just mentioned, I also have another question. I mean, usually when you define the Mellin transform in higher dimension, you don't actually get crossing symmetry. You can actually find, you can write down objects that do not have any crossing symmetry. And but here it seems that you are imposing crossing symmetry at the level of the Mellin transform. So what's the motivation for this? We
impose that because we can actually, at the beginning we tried with crossing symmetry, with crossing symmetric D function, also to just try to find something consistent. And so we thought that that was the easiest way, but we also applied this to non-crossing symmetric D bar function, and it seems to work.
I see. So basically what you're saying is that you have still a polynomial of this S that is related to the contact interaction, but the mapping is not as simple, in the sense that a phi to the 4th is mapped to a polynomial, and some other polynomial is mapped to some other derivatives and so on. So the map is not the same, as simple as in higher dimensions, but it's similar.
It's similar, yes, but we don't actually think that there would be just a constant. It seems a bit more.
And so this is my last question, and then because also time is running out. I mean, usually these gamma functions that you mentioned in higher dimensions, they have some interpretations in terms of double trace operators. Can you have a similar interpretation for the poles of this gamma function you have here, or the interpretation is different?
We think that the interpretation is similar. Yeah, it should be so the same.
They are poles associated to each double trace operator.
Yes, we checked and it seems to work the same.
Okay, if there is no other question for Giulia, we can thank her for the nice talk, and we can move on to the next talk.